the recording. And here we go. So this particular section is about atomic structure, elements, and molecules. That's what the whole section is about. And it begins with atomic structure, atomic number, and atomic mass. And here, if you are wondering, that doesn't look like Tony's writing. It's not. It's my daughter's writing. I gave her the task, the coronavirus task of writing this for me. She writes a little bit differently than me. And here she's writing really tiny and very neatly. I've asked her to write a little larger in the future, but as neat. So the goals of this particular portion of the text are to describe electrons, protons, and neutrons, and the general structure of the atom, and define the terms atomic number and mass number. So let's take a look. Now, this is not something that you have in your book, but it's something I drew. This is an atom. Atoms don't have circles around them. The circle is just kind of to show you the space where you would find electrons. The little dots you see here are electrons. And here's my little legend over here. The dots are electrons. The solid spheres are protons. And the white or empty spheres, if you want to call them, are neutrons. And this thing is not drawn to scale, but it shows you what we consider to be the current structure of an atom. We think of it as a sphere where the electrons are somewhere around the nucleus, and the size of the atom is really defined by the space where the electrons are, not by the nucleus. Yes, the nucleus is at the center of the sphere, and I know you take that for granted, but when people were first trying to figure out what the atom was, they put the nucleus in the corner of a cube. Doesn't make sense for a lot of reasons, and they settled on, let's put the nucleus at the center of a sphere. And these are really intelligent people having these discussions. It's not like a nonsense. They had to decide, where are we going to put the nucleus in an atom? What shape are we going to give it? Now, for the scale here, to give you an idea of the scale, something that you can appreciate, if you think of the nucleus as being a pea, the size of a pea, the place where you would find the electrons compared to that pea would be like a football stadium. That's how different they are. So the place where you find the electrons has a diameter, if you will, that's 10,000 times greater than the diameter of the nucleus. So it's kind of interesting to think that an atom is mostly where the electrons are, and it's mostly space. And we're going to get to that later. So here's properties of subatomic particles, the particles that are smaller than an atom. So we have the electron, we have the proton, and we have the neutron. And here are two different symbols for each. We will learn more about these symbols where I have a -1 at the bottom and a 0 at the top. Basically, the bottom at the number in this case is the charge on the particle. So the electron has a -1 charge, the proton has a +1 charge, and the neutron has no charge. Okay? We also write the symbols this way, where we don't write these numbers in front, but we write the charge off to the right. And I usually circle the charge to accentuate it. Your book doesn't. And for 0, I write a little line through it to accentuate that. The location of each of these is that the electron is found in the space around the nucleus. It's a spherical space. Protons are found in the nucleus, and neutrons are found in the nucleus. Now, here's some really interesting information. And I would not memorize these numbers here that I'm pointing at. That is, don't memorize the mass in grams. So the interesting things about these masses is that if you look at the mass of a proton and the mass of a neutron, they differ by 2 out of 1,000. Actually, 2 out of 1,600, 1,700. So that's like they differ by 1 out of 1,000. In other words, they're basically the same mass. However, when you look at the mass of the electron and you notice that this is -28 compared to -24, turns out that the electrons are 2,000 times less massive than the proton or the neutron. Now, These are numbers you should memorize. The relative mass of each of these is 1.00 for a neutron, 1.00 for a proton, and 0 for an electron. A relative mass is just a mass where you just pick a number and you say, hey, we're going to make everything relative to that. So there's something called the TU, the Tony unit. It's a relative mass, and everything is measured relative to me. So I weigh 200 pounds. If you weigh 100 pounds, you would be 0.5 TU. If you weighed 150 pounds, that would put you at what? 0.75 TU. It's rapidly gaining a popularity because everyone likes the TU, except for a few people. And the problems with the TU is that, well, it changes. 30 years ago, the TU was 150 pounds, and now it's 200 pounds. So the TU keeps changing, and who knows what's going to happen in the future. So that's why the TU is not very popular, but it's just a relative mass. So this is a relative mass called the atomic mass unit. And if you haven't noticed, chemists really love to abbreviate things. Even so, to the point where we will abbreviate an abbreviation. So there is an abbreviation for this abbreviation, atomic mass unit, and the abbreviation is U. Now, the charge on each of these. The charge on an electron is -1. Charge on a proton is +1. Charge on a neutron is 0. Now, let's look at some charge properties. So there are two types of charges. There's positive charge and there's negative charge. For positive charge, we use a positive sign. For negative charge, we use a negative sign. There are two amounts of charges that we use in chemistry, and that is +1 and -1. You'll find that when you take a physics class, there are charges based on coulombs that are not whole numbers, but here we either have a +1 or a -1 when we talk about charges. And so this refers to, of course, the proton with a +1 charge, the electron with a -1 charge. You also need to know that like charges repel. So if you happen to have two electrons near one another, they will repel one another. Two protons near one another, they repel one another. A proton and an electron, and they attract one another. Now, if you look at this and you find out that, oh, protons repel one another, so what's going on with that drawing you had there before, Tony? You got those protons near one another. Aren't they repelling one another? And the answer is yes, they do. So what keeps them from repelling one another completely? And the answer is simple. They've got a buffer of neutrons in there. So that's one of the proposed reasons why you have neutrons. It's to buffer the protons from repelling one another. Okay. And you also need to know that charges are additive. So here, when we have 9 electrons, each electron with a each electron with a -1 charge, 9 electrons would be -9 total. 9 protons, each proton with a +1 charge would be +9 total. So you have -9 here, +9 here, that equals 0 charge. But if you had an atom with 10 electrons in it and a -10 charge, and 9 protons in it, +9 charge, you'd have -10 +9. That atom would have a -1 charge. So you need to know there's two types of charges. Their amounts are +1 and -1. Like charges repel, unlike charges attract, and charges are additive. So here's some terminology that you'll need to know for the rest of this chapter, for the rest of chemistry. You need to know this stuff. All right. So the nucleus, that's your center of the atom, has nucleons in it. That seems like a very appropriate name. You find nucleons in the nucleus. You find Martians on Mars. You find Moontians on the moon. So I kind of like this nucleon. Maybe it should be Moonchions. All right. Protons are a type of nucleon. Neutrons are a type of nucleon. There's the electron cloud. That's what we call that region of space where you find the electrons, an electron cloud. Sometimes it's called an electron region. Both are just fine. Atomic number. This is the number of protons in the nucleus of an atom. Each element has a specific atomic number. The symbol for atomic number is Z, and you're going to have to live with that. I'm sorry there's no Z in atomic number, but that's just the way it is. There's relative atomic mass. This is the mass in atomic mass units. This is that relative mass we use for measuring protons and neutrons and electrons. And if you want to know how much relative atomic mass is, it's 1.661 times 10 to the minus 24 grams. And if I pull up that chart from earlier to show you the mass of a proton and a neutron and compare it here. So here's the mass of a proton and a neutron. You can see that these values are very similar, and that's why I have 1.00 here. Okay. Mass number. This is the number of nucleons in an atom. So the number of protons and neutrons, and it's represented by the symbol A. So this is how you write the symbol of a particular atom of a molecule, or excuse me, of an element. X represents the symbol. So it could be H for hydrogen, He for helium. A is the mass number, and Z is the atomic number. And here, I think the reason they made A the mass number and Z the atomic number is because this looks better with A at the top and Z at the bottom, kind of like an alphabetical order. Okay, so A is mass number, Z is atomic number. Okay, so here's a problem from the book that has been copied. What is the composition of an atom of phosphorus with 16 neutrons? What is its mass number? What is the symbol for such an atom? If the atom has an actual mass of 30.9738 U, so there's that abbreviation for atomic mass unit, what is it in grams? And finally, what is the mass of this phosphorus atom relative to the mass of a carbon atom with a mass of 12? So let's deal with these one by one. What is the composition of a phosphorus atom with 16 neutrons? Well, we're going to need our periodic table to do this. So here it is. And here is phosphorus right here. So let's zoom in on that phosphorus. And then focus. So the phosphorus is right here. And I'm going to write this down. P 15 30.97. And I'm going to take this card away and I'm going to zoom out so you can see what I have written. Okay, so here's what I've written. So in answer to the question, what is the composition of an atom of phosphorus with 16 neutrons? Well, we would say that the number of protons is equal to 15. So you will usually find that at the top of the element in the periodic table, number of protons. It will be the number that is a whole number. So it's got to be 1, 2, 3, 4. You can't have less than one proton, and you can't have negative protons. So it's going to be a whole number. Now, the number of neutrons is given 16, and the total here is 31. Okay, so this is the mass number. Because it's important to know that the mass number is the total number of nucleons. So 31. So this is the answer to its mass number, and this is the answer to the composition. Now, one of the things we didn't address with this composition is, what about electrons? How many electrons does it have? And here's what you're going to do. Unless you know otherwise, you're going to assume you have a neutral atom. So if we have a neutral atom and it has 15 protons, it has to have 15 electrons. And here we're assuming that it's neutral. Okay. All right. So we have checked off the first one. We have checked off the mass number. What is the symbol for this atom? Well, remember the symbol is this. And if you get confused with the A and Z, just remember this. You put the larger number on top. So here we're going to put phosphorus. We're going to put the mass number on top and the number of protons on the bottom. So that is the way to write the symbol for this element. And I'm going to teach you one more way to write this element. You could also write it this way. These represent the same atom. Why did we leave the 15 off? And the answer is, well, because you can find that on the periodic table. It's at the top. Why did we write the 31 in? Well, because that is not on the periodic table. 30.97 is on the periodic table, but we don't round that up to 31 and say it's 31. This is exactly 31 pieces, not 30.97, exactly 31 nucleons. So that's two ways of writing the symbol for this atom. So we've checked off that one. If the atom has an actual mass of 30.9738 U, what is its mass in grams? So we take that 30.9738 U, and we want to convert that into grams, which means we need to know that 1 AMU is equal to 1.661. And I don't memorize this number. I always look it up. Actually, the book gives us a better value than this. I don't remember what it is. Times 10 to the minus 24 grams. So I'm going to use that. So I would write 30.9738 U times here. One of these has to go in the denominator. I'm going to put the 1 AMU in the denominator. We're going to make it U instead of 1 AMU. And I'm going to put 1.661 times 10 to the minus 24 grams in the numerator to get the answer. Okay. Now we have 30 point, well, we can estimate the answer, right? 1.6 is roughly 1.5. 1.5 times 31 is roughly 45. A little bit more, so we'll call it 47. So we have 47 times 10 to the minus 24, which becomes 4.7 times 10 to the minus 23. So our ish is 4.7 times 10 to the minus 23-ish grams. Here, with this calculation, we'd be allowed 4 significant figures in the answer, so let's find out what it is. So here's my calculator. Here's the 30.9738 times 1.661 second EE negative 24. And we get, the actual answer is 5.145 times 10 to the minus 23 grams. My ish is a little farther off than it's been in the past, but that's still okay because roughly 4.7 and 5.1 are pretty close to one another. They're within 10% of one another. And that's what you're hoping for with your ish, to get within 10% of the real number. We got the same order of magnitude for the 10. So that's how you would do that. And then finally, what is the mass of the phosphorus atom relative to the mass of a carbon atom with a mass of 12? Well, here's what we would do for the carbon atom. We can answer it two ways. The carbon atom with 12 would have a mass of 12 AMU, right? And actually, we would say 12.0 AMU because we know that every nucleon weighs 1.00. 1.00 has 3 zig figs times 12, and you get 12.0. This is exact because it's counted. It's based on that, okay? All right, now if we wanted to turn this into grams, we would take that 12.0 U multiplied by the 1.661 times 10 to the minus 24 grams per 1 U. And we could estimate this again, 1.661 times 12 has got to be around 21. So my new-ish is a 21 times 10 to the minus 24, or 2.1 times 10 to the minus 23-ish. And let's see what we actually get. 12.0. I should show you my calculator. Times 1.661 second EE negative 24. And we get 1.99 times 10 to the minus 23 grams. So we could answer this two ways. The mass is 12 AMU relative to 31 AMU, or 30.9738. Or we could say that these are the relative masses. Now, these aren't really relative because we're using grams. These are relative because we're using these relative units, 12 AMU and 30.9738 AMU. Okay, so there we go. Isotopes and atomic weight. So we're going to be discussing isotopes of elements and atomic weight, sometimes also called atomic mass. We want to be able to define isotopes and give the mass number and number of neutrons for a specific isotope. And we want to perform calculations that relate the atomic weight or atomic mass of an element and its isotopic abundances and masses. So here's what I have for isotopes and atomic weight. When we talk about isotopes of an element, these are atoms of an element with the same number of protons, but a different number of neutrons. So they have a different mass number, which is represented by the letter A. Each element has at least one isotope. Most have multiple isotopes. And it's kind of interesting when you look at the isotopes. Hydrogen, for instance, has 3 isotopes: H1, H2, and H3. And people might ask which one is the main isotope, and that's kind of an inappropriate question. You should think of the word isotope like being a substitute for twins or triplets or quadruplets and so forth and so on. You wouldn't approach a group of twins or triplets and say, which one is the main one and which ones are the copies, right? So you don't use isotope that way. Every atom of an element is an isotope of that element. There's at least one, and often there's multiple. You can't look at the periodic table and tell how many isotopes an element has just by looking at the periodic table. It can't be done. And we don't memorize the isotopes of elements. It's not worth it. Now, the isotopes of the elements are not usually in equal proportions. So if you have 2 isotopes, it's not usually 50% of one and 50% of the other. It might be, well, you got 4 parts of one and 2 parts of the other. Okay, so they're often not in equal proportions. And that means if you have 3 isotopes, it's not going to be 33, 33, 33. It'll be like maybe, I don't know, 99, 1, and 0. Okay. Here, natural abundance, I sometimes use the abbreviation PA, and the sum of the percent abundances should be 100%. There's also the natural fractional abundance, and the sum of the fractional abundance equal 1. To get the fractional abundance, you take the percent abundance and divide it by 100%. One of the things I don't like is when people move the decimal over 2 places when they have a percent. And there's a reason for that. So I'm going to pull out a piece of paper here. And let's say that you have this number 0.0032%, and you want to move the decimal over. Your 2 choices are to make this 0.32 or to make it 0.000032. Okay, so you got to move the decimal over 2 places. Which one of these is correct? And for me, it's a no-brainer. It's a no-brainer. This one's correct and this one's wrong. How do I know that? Because I know that the definition of percentage, by definition, means out of 100. So this is what percentage really means. If you get rid of that percent, you put 100 on the bottom. Now, if I divide 100 into 0.0032, is the result going to be bigger than 0.0032 or smaller? And the answer has to be smaller. So don't bother memorizing whether to move the decimal over to the left or right. Memorize the definition of percentage. It's really easy. Percentage is that number divided by 100. And then use that definition and you won't make a mistake. Okay, so hopefully your math teacher told you why you're moving that decimal over, which way you're moving it, and why. Just put it over 100, problem solved. All right, let's take a look at symbols of isotopes. I've already spoken about this before, but I wanted to make it as plain as I can, using boron as an example. Boron has 2 isotopes, each has 5 protons. One has 5 neutrons, the other has 6 neutrons. So here are the 2 standard symbols. So we're going to call this the standard symbol. Okay, and here, this is the abbreviated symbol, if you will. So on an exam, if I asked you for the standard symbol of an isotope, I'm looking for this guy right here. Okay, that format. So notice here that in the standard symbol, you show the mass number on top, you show the atomic number on the bottom, and then you write the symbol to the right of those two. And when I say top and bottom, this is really superscript and this is subscript. And it turns out that if you wanted to type this into a document using Word, it's pretty easy. You just use Equation Editor and you play around with it. And you'll find that there's a little thing on Equation Editor where it asks you, do you want this guy? And you click yes, and you fill in the cubes, and you're good to go. Okay, now this abbreviated symbol was made because chemistry has been performed for hundreds of years, and textbooks about chemistry have been written more recently in the last 150 years that were commonly distributed to students. And writing something like this in a textbook is really difficult to do because textbooks are often made with typewriters and things like that. And to do a subscript and a superscript with a typewriter is really painful because you got to turn the roller half a turn, type the 11, and then you have to turn it half a turn, type the uppercase B, then you have to back it up a space and turn the roller the other way and type the 5. A pain in the rear with a typewriter, a lot easier with a computer. So before computers were invented and you're writing textbooks, how do you write something like this so that people know what you're talking about? You simply write it in this abbreviated format. So this is like the pre-computer way of writing isotopes out, and it's still used today. All right, so these are the 2 isotopes of bromine. Now, this is not a question that's in the book, but it's one I'm going to propose to you. So here is the symbol of bromine, and it's got a 5 at the top. That's the atomic number, the number of protons in the nucleus, and it's got a 10.811 in the bottom. So looking at that, that is your average mass of a bromine atom, if you take into consideration that it's not necessarily 50-50%. Okay, so if we look at this, which of these isotopes is more abundant, B10 or B11? Well, here's how you do it. The mass of B10 is 10 AMU. The mass of B11 is 11 AMU. And when you look at these two, and if you average them, you get 10.5 AMU. But what if there were more B11s? Well, the average would be closer to 11. What if there were more B10s? The average would be closer to 10. So 10.5 is the cutoff where it'd be 50-50 because it's halfway between those two masses. This is clearly beyond 10.5. It's closer to 11. So our guess would be that there would be more boron than there would boron 11 than there would be boron 10. Okay? All right. So let's look at atomic mass of an element. This is the mass of your average atom of an element, NAMUs, based on the abundance of each isotope and the relative mass of each isotope. So that means you need the relative mass of each isotope and you need the abundance to be able to do this. The abundance in mass is found using mass spectrometry, and we'll be talking a little bit more about mass spectrometry in a lab next week called mass spectrometry. The average weight, or the atomic weight, I should say, of an element is the sum of, so this means sum of, the isotope mass times its fractional abundance. So let's take a look at a problem. This is an example from the book. This says, calculate the atomic weight from isotope abundance. So we have bromine has two naturally occurring isotopes, one with a mass of 78.928338 U, an abundance of 50.69%, and the other isotope has a mass of 80.911 or 80.916, blah, 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 blah. Calculate the atomic weight of bromine. So let me show you how to do this very methodically so that it's very easy to follow what's going on. So first of all, I'm going to put AW for atomic weight, and then I'm going to put bromine in parentheses here. And then I'm going to put times the mass of bromine. So two naturally occurring isotopes. Do you see that this mass is really close to 79? That means that the mass number of the bromine is 79. Now, here's an interesting question. If it does have 79 nucleons, wouldn't that be 79.0, not 78.9? And the answer is, yeah, it would be, but turns out that something happens in the nucleus. And what happens is that some of the mass is actually turned into energy to bind the nucleus together. It's called the binding energy of the nucleus. And that mass is turned into energy. So when you lose that mass, your mass ends up being a little smaller, okay? That seems to go against the idea that you need to conserve mass and need to conserve energy, but remember, we're just changing those things into one another. Okay, so we have the mass of bromine 79 times the fractional abundance of bromine 79 plus, let's take a look at that isotope. What is the mass of that one, the mass number? Well, 80.9 rounds to 81. So the isotope is bromine 81. Okay? Times the fractional abundance of bromine 81. And you know what? I don't like that little line there after fractional abundance, so I'm going to use my little whiteout here and get rid of it so that it looks nicer. So now let's fill in the blanks. What is the mass of bromine 79? It's 78.918338 U. Notice I keep the unit there. Now, what is the fractional abundance of bromine 79? It's 50.69% over 100%. So the definition of percentage is it means it's over 100. So that's what I've just done. It's far better than moving the decimal over two places. And then we have 916,291 U. And then we have 49.31 divided by 100%. Okay, so now we do the calculations and we can kind of estimate the answer, right? 50 over 100 is 1/2. What's 1/2 of 79? It's close to 40. So this answer should be close to 40. Here, this is also 1/2. What's 1/2 of 81? The answer should be close to 40. So our ish says 40U plus 40U equals 80U, and that's what we expect for the final answer, around 80U, 80-ish U. So let's actually do this on our calculator. On 78.91833 times 50.69 divided by 100. And so here we get 40.0037. I'm going to put 40.004U. And I'm going to put an arrow going down to that zero there because 50.69 has 4 significant figures. The definition of percentage means over 100 exactly, so that's infinite numbers of figs for the 100. And here we have 1, 2, 3, 4, 5, 6, 7, 8. We have 8 significant figures. So the deal is that I want to keep at least one extra figure that's not significant before I finally round. So you don't need to carry on all of those figures. It's just too much work. 0.916291 times 49.31 divided by 100. And here we get 39.8 998. Here, I'm going to keep a little extra here. Oops. 39.8998. I'm going to put my arrow to right here. And the reason I kept the extras because I saw that if I rounded this, I'd have to round it to 39.90. But nonetheless, can everyone see that I should have rounded to 2 places after the decimal here, rounded to 2 places after the decimal here. And so now when I add these, I'm going to round to 2 places after the decimal for my final answer. So plus 40.004, and we get 79.90U. And that's the atomic weight of bromine, rounded to the appropriate place, showing the work I would expect if this were a question on the exam. So you should try this also. What I mean by that is you should read the sample problem, look at the information they give, and see if you can come to the same conclusion. If anything, this might help you do a problem like this. So you might say that you make a little list of the masses, 78.918338U. And we have the percentage is 50.69%. And then for the other one, you have a mass of 80.916281U and 49.31%. Maybe you make a little list because it's easier for you to grab from a list. Take a look at these percentages. When you add them together, what do you get? 100%. Okay, so here's another example. I'm going to leave this up here for just a minute. I'm not going to show you how I figured all of this out. This is just another example of showing you the type of work I'm expecting and where to round appropriately. Now, there are 3 isotopes of hydrogen, H1, H2, and H3. Here are their masses in AMUs, and here's the percent abundance of each. Now, this is an interesting one. The percent abundance of H3 is 0, which makes you think that it does not exist, okay? These fractional abundances are written a little off kilter here. It doesn't mean it exists. When you talk about a percent abundance of 99.985, you're really talking about a sample size of 100,000. So if you had 100,000 atoms, 99,985 would be H1, 15 would be H2, and 0 would be H3. It turns out that when you reach in and you grab hydrogen atoms and you grab only 100,000, you're not likely to have an H3. That's what the 0 means. Not that they don't exist, but the sample size is too small for you to actually get one. It's kind of like if you looked at the population of the United States Or actually, if you take a look at the population of, say, Eureka, and you look for the person who is 7'5", what's the likelihood of someone being 7'5" in Eureka? Probably not very good. All right, so the sample size is too small. All right, so here again, you can replay this video and look at this work. And what you might want to do with this is copy these numbers down and see if you come to the same conclusion that I do. Okay, this one is a tougher one, calculating isotopic abundances. So antimony has two stable isotopes. One of them is antimony 121 with a mass of 120.904 U. And the other one is antimony 123 with a mass of 122.904 U. And we're asked, what is the relative abundance of each of these? Well, when I look up antimony on my periodic table, this is what I find for antimony. I find that the number at top is 51, and the number at bottom is 121.8. So based on this alone, which one of these is likely to be more abundant? Well, I can make a little number line here. So I'm going to call this 123, 122, 121. So this is antimony 121, and this is antimony 123. And this number 121.8 is going to be right here. So since that number is closer to 121, I think that antimony 121 is going to be more abundant. So how do we set up a problem like this? Well, we set it up the same way we do everything else. And so here we would have that the atomic weight of antimony is equal to, in this case, we know the answer, 121.8 U, and that's going to be equal to the antimony 121 mass times the fractional abundance of antimony 121 plus the mass of antimony 123 times the fractional abundance of antimony 123. Now, do you recall that I told you that when you add up the percent abundance of these two, you get 100%. What happens when you add up the fractional abundance of each of these? You get 1, and that 1 is exact. Okay, so the way you kind of handle this is you could say that this is X, and this is Y, and this is 1, right? Or Y is equal to 1 minus X. And what we're really saying here is that the fractional abundance of 123 is equal to 1 minus the fractional abundance of 121. Okay, so let's take a look at this, at what we have above here. So we have 121.8 U is equal to the mass of 121, which is 120.904 U, times the fractional abundance of 121. And remember, we said we're going to call that X, plus the mass of 123, which is 122.904 U. And we're going to call this guy Y. Okay? Now, we also have this here, Y is equal to 1 minus X, so we can write 121.8 U is 120.904 U times X plus 122.904 U times 1 minus X. Now, when we take a look at this, the U's cancel because they're in every term that's being multiplied together. And we just end up having one equation with one variable, and you solve for X. Now, rather than put you through the paces here with all the algebra, I'm going to let you work this out, see if you can get to the correct answer. We should find out that for X, which is the percent of antimony 121, should be a little bit bigger than antimony 123. And just looking at the numbers, I would guess that antimony 121 might be like 60% and the other 40%, something like that. So this is the kind of work you would show. I'm not going to show you the rest of it because it's just algebra, which you are great at. Let's look at the discovery of subatomic particles. This is a little bit of a history lesson. It's pretty interesting. The discovery of the electron was in the late 18th century. So we're talking about, I don't know, was it the 18th century? It was around 1850, 1860. So 19 was the 20th century. So this would actually be the 19th century. Okay, and it was discovered with the advent of this thing called the cathode ray tube, which is basically an electron gun developed by a guy named Crookes. And in this experiment, they found the charge to mass ratio of an electron was really, really small, which means it's smaller than the smallest known atom at the time, which is hydrogen. I should tell you that hydrogen is still the smallest atom. So they found a particle that's smaller than an atom, so they suspected that this was actually part of an atom. Radioactivity was also discovered in the late 19th century by a guy named Henri Becquerel in France. Someone gave him a rock and said, this is some really interesting stuff. He put it in a drawer, and in this drawer there are also photographic plates that would turn dark when they were exposed to light. Turns out that the photographic plate wasn't exposed to light, but he pulled it out of the drawer and it had an image on it, an image of the rock. So he figured out that the rock was somehow shining light energy at the photographic plate. So there was something going on there, and he basically handed the stuff over to a very famous scientist named Marie Curie and her husband Pierre, and they pushed forward the study of radioactivity quite a bit. And it's suspected that they both suffered from radiation poisoning during their lives. I believe Pierre did not die from radiation poisoning. I think he was in an auto accident of some sort, like run over by a car. Marie Curie, I think, died due to complications due to radiation poisoning. There's the Millikan oil drop experiment. So here they didn't determine the charge to mass ratio. They actually figured out the charge on an electron, and combine that with the charge to mass ratio, you can actually find out the mass of an electron. And then there's Rutherford's gold foil experiment, which is really cool. Before Rutherford, Thomson thought that matter was basically like a plum pudding model. So we knew about electrons, and he thought, well, electrons are these little plums inside of pudding, and the rest of the atom is just this amorphous solid. So Rutherford thought, well, you know what, if that's true, I'm going to take this radioactive particle and shoot it through that plum pudding, and it should be able to rip right through the plum pudding and end the story. So he shot alpha particles at gold foil, and you might ask, why use gold foil? And the answer is because you can make it really, really thin, because he was thinking if the material was too thick, the particle wouldn't make it through, so he'd make it really thin. And metal is something that you can make very, very, very thin. Also, it's unreactive. He didn't want the alpha particle to react with the gold, and gold is unreactive. That's why it makes great jewelry. And he found out that when he shot the particles through the gold, most of them went right through, just like the plum pudding model expected. What happened unexpectedly, though, was that a number of the particles veered off to the left or to the right, and some veered right back. So he had to come up with a better explanation. The better explanation for why most particles go right through the atom is that, well, an atom is mostly space. Why does some bounce back? There's something massive inside an atom that shoots the particles back. And so that's how we got our current idea of the atom, where we started this particular lecture. Now, the next section is the periodic table. I think I've gone on long enough for right now. And this is where we will begin the next lecture, which will be Friday. So right now I'm going to pause this lecture. I'm going to stop the recording actually.